Go ahead.
Thank you, Max, and good afternoon or good morning to all of you. I looked over the attendance list from the first session, and we had several people from South America, several people from Africa, from Europe, and at least one person from Australia. So I'm glad that the materials are getting out there and getting to you. The note in the purple box is that these materials are for undergrad and grad students or faculty and teaching assistants. So if you are working full-time in industry, oil and gas or otherwise, I would ask you to leave the webinar at this point and not to visit the website. This is one slide I showed last week or last session on Tuesday. I forgot to make a point about this. It shows the two courses that are on the IRIS website. The first one I gave last fall, 34 lessons, and now we're in the midst of 8 lessons on petroleum exploration, a field example. Let me tell you the difference between the two. The first one with the longer number of lessons is more of a topical course. And so it talks about different parts of our business, seismic acquisition, well logs, well seismic ties, seismic attributes. If I use the analogy of a person in home construction, the first course is telling you this is a hammer and this is a screwdriver and this is a saw. The intent of the second is to show the workflow, how all these things can be put together to analyze a basin in the early part of the exploration phase. So now that I know what a saw and hammer and pliers are, how do I build a house? So hopefully that's helpful. There was one question that was asked just as we were signing off on Tuesday. The question, do source rocks have valuable amounts of oil and gas, or are they useless? They certainly are not useless. We do have to talk about conventional fields, which are the things that the industry's been looking for over 100 years, and resource plays or unconventional fields where we are trying to get oil and gas out of very tight, low porosity, low permeability rocks. So in a conventional setting, source rocks are valuable in regards to generating hydrocarbon that's then going to migrate to our conventional reservoirs. In the unconventional or resource plays, the source rocks are the things that we are trying to tap into. And an example of that along the Gulf Coast in Texas, we have the Barnett Shale. For many decades, the Barnett has been considered a source rock, but we did not drill and try to complete and produce fluids out of the Barnett. That changed about 10 years ago. 2 technological advances allow us now to go after these tight reservoirs. The first technology is directional drilling. So the fact that we can put a well bore that goes through, not vertically through the Barnett, but goes along the Barnett for thousands of feet. And then the other technology is fracking, so that we can allow the oil and gas in the tight rocks to actually move and come up the pipes. So lecture 2 is about regional data. And when we're looking at an area, especially in the early exploration phase, we want to capture as much information as we can about the basin we're looking at and the hydrocarbons that may or may not be present there. So we'll look at geological maps. We'll look at the plate tectonic history of the area. We may have gravity and magnetic data that we can use. We'll typically have regional seismic lines. These days, we may have a denser 2D grid of data. And even in some areas of exploration, they start with 3D seismic. We want to look at the tectonic evolution of the area. we want to put together a stratigraphic chart, such as shown in the upper middle. We may put together some paleogeographic maps and anything else that might help us understand and unravel the geological history and then be able to interpret the potential to find oil and gas. So there's a couple of images on here. This is a regional 2D seismic line. It's a classic. It's called Line C, first published in 1977 in AAPG Memoir 26. We have a stratigraphic chart. This is a satellite gravity-based bathymetric map of the South Atlantic. And on the right, we have a reconstruction from late Jurassic up to the earliest Tertiary of the South American margin. So those are the types of information that we would want for a regional or mega-regional analysis. These types of regional analyses are important. They can help us decide which basins on the planet hold the highest potential for discovering and producing new oil and gas finds. They provide a regional context of how the basin has formed and subsided and gotten infilled with sediments, so we can understand important characteristics about the region. It can provide some geological constraints and the likelihood that hydrocarbons either are or are not present in the area that we're looking at. If we're in the very early part of exploration, where some blocks are up for lease and we're trying to decide if we want to bid money and try to win a block or 2 or 6 or 10. And the regional analysis can help us with step-out wells. Once we have made a discovery, where else in the vicinity should we be drilling, trying to find similar types of oil and gas deposits? Some of the questions that we would ask and try to answer, are there any known hydrocarbon occurrences near the study area that we're looking at? What's the availability of outcrop data and well data and the geophysical data that we would have for the area that we're trying to analyze? What's the plate tectonic history for this particular area, this basin or sub-basin? And that would include the timing of some of the major tectonic events and maybe how intense or minor some of those events might have been. What does the local stratigraphic chart look like? What sorts of ages of units and what sorts of environments of deposition, and where might we have some of the play elements that I talked about on Tuesday? Where might there be source intervals? Where might there be reservoir intervals? Where might there be trap intervals? Do I have a possibility to have mature source rocks that are generating oil and gas, either in the past or up to and including the present day? Are there reservoir quality clastics or carbonates that I expect to have in my area of study? How likely are regional seals in this particular basin or sub-basin? And one of the questions that's important for us as exploration is, what's the weakest play element in a particular area? If I'm in a basin like the US Gulf Coast, where we have a lot of good sandy intervals, it might be the presence of seals that is the most limiting factor of the play elements. So instead of having a study where I'm focused on reservoir, I may spend more time worrying about regional seals and trying to understand what part of the basin I might be most interested in, or where I might drill an exploration well. For the local data within our study area, whether that's onshore or offshore, we can have certain types of information data that comes from the surface. Onshore, we'd have topographic maps. Offshore, we have bathymetric maps. We may have surface geology showing structure and stratigraphy. A geologic map of a land area would be an example of that type of information. We may have outcrops that are close by, or we may have analogs. A lot of people working offshore West Africa are exploring for and producing from deepwater turbidites deposited in deepwater fans. And so a lot of these workers will take field trips to San Clemente, California, where there are beautiful outcrops of these types of deepwater turbidites. And so they can take information that they can glean from this analog outcrop and hopefully have a better understanding as to how deepwater sands off of West Africa are going to behave. We might have heat flow measurements. We might have hydrocarbon seeps, and there are various other types of local surface data that we may be able to benefit from. We can also have subsurface data in our area of study. That can be from well data. We may actually have cores that were collected when the drilling was going on. We could have cuttings, which are the shavings that come up with the circulating fluid. If we have wells, we have probably run some type of a log in which we are capturing certain types of physical properties. From the well data, we often can determine lithologies. If we have microfossils, we may be able to figure out geological ages. If we collect samples, we may be able to get some of the geochemical properties. Last Tuesday, I mentioned total organic carbon and hydrogen index as two of the geochemical types of parameters that we would like to have for potential source intervals. And then we have geophysical data. We have seismic data. It could be 2D lines. It could be a 3D volume, or it could be 4D or time lapse. In exploration, we typically don't have 4D data, but if we're working a field production question, we may have 4D or time lapse seismic. We may also have gravity data or magnetic data, or we may have seismic, gravity, and magnetic data for our area of study. So that's the first lecture on regional data, regional analysis. I'll pause here for a moment, and if you have a question or would like clarification, you can type that into the chat section of the GoToWebinar control panel, and Max will relay that verbally to me. So let me go on. If you do have questions, do send them in to Max. I do not see the questions, only he does, and he will pass those questions on to me as we have breaks in the three-part presentation today. So what I'm going to do is I'm going to show you some regional geological information analysis for the Gippsland Basin, the area that we are going to focus in on as we study a particular historic field. And as I mentioned last Tuesday, we're in the area of Australia. This is the island of Tasmania, and where the little white box is, that's the Bass Straits. And under the Bass Straits, we have a portion of the Gippsland Basin. The Gippsland Basin is 1/3 onshore and 2/3 offshore. And so we have the availability of onshore exposures of the rocks that we are interested in prospecting in the offshore blocks. And the lighter blue squares are the offshore blocks, not actual, but theoretical, that the government of Australia is offering up for lease. And so we want to analyze this area and see out of these 35 blocks, 28 blocks, however many there are, if there are any that we are most interested in. We are interested in mostly Oligocene age rocks for our source, for our reservoir and our seal, and Eocene to Oligocene for our source. I'll talk more about that in a little bit. We have a number of outcrops where those age rocks are exposed in the hinterland. We have one gas field that is economic down here, and we have a set of widely spaced 2D seismic lines in the offshore to try to do our analysis. So a certain number of offshore blocks are being offered by the government. A third of the basin is onshore, where we can get some information. There are no wells offshore. There are a number of wells that are onshore. So from the onshore data, we can determine things such as the tectonic history. This is an extensional or pull apart or Atlantic margin type of basin. The rifting began in the later part of the Cretaceous, and the rifting continued until about mid-Oligocene time, when the extension stopped. Let me go back for a second. There's a triple junction in the area of this white box. There is extensional rift present day that goes through south of Australia, separating Australia from Antarctica. And then there's a transform strike slip margin over here. The Gippsland is an extensional rift basin that was the third arm that was the one that's going to eventually fail. And so we have a fancy geological term for a failed part of a triple junction, and that is an Oligocene. So when the extension in the Gippsland Basin ceased, that's when the extension stopped occurring. And in essence, the area rapidly collapsed as we take away the tectonic driving force of the extension and the heat from the mantle that's associated with that. From the onshore outcrops and wells, we can put together a stratigraphic summary. Here's a stratigraphic chart from inland to coastal. The Pleistocene is thin, fluvial deposits. We're really not interested in that. The Pliocene also is fluvial. We're not interested in that. The Miocene contains some offshore carbonates. This isn't really part of our exploration target. The early Oligocene has some deep water shales, and I'll talk more about them. Those are going to be our sealing lithologies. And then the late Oligocene is fluvial to near shore deposits, and we have good quality fluvial sands and good quality near shore. If you prefer beach as a term, we have good quality sands. So the geological history in early Oligocene, there was a regression. The paleo shoreline was close to present day shoreline. A major unconformity occurred near the mid-Oligocene at the time that this rifting ceased and the area collapsed. The area subsided very rapidly, and there was a major transgression putting in the deeper water shales. That's going to be our seal. During the Miocene, reefs developed in this area, and so we had good carbonate deposition. And then in the Plio-Pleistocene, there was another regression, and the shoreline occupied its present position and covered the deeper water deposits of the shale and the offshore carbonates. So we have a major unconformity. The fluvial and nearshore deposits are called the Latrobe group or Latrobe Formation. The overlying deep water shale is the lake entrance, and there should be an S there, sorry, formation. And so there's a big unconformity that separates the Latrobe from the lake entrance, and that unconformity is referred to as the top of Latrobe unconformity, or TOL for short. So as I mentioned, Gippsland Basin was part of a triple junction. Active rifting ceased in the early Oligocene. This failed rift sank very rapidly. We had rapid subsidence and flooding, and later on we had some tectonic readjustment. The early Oligocene Latrobe Formation, that has fluvial to near shore deposits, and that's going to be our potential reservoir rocks. And then the late Oligocene lake entrance formation, that consists of deep water shales, and those are going to form a fantastic seal. So we have extensional fault blocks that will set up our traps. So we'll be looking for anticlines, some of which are fault dependent, as this one is. We're going to be looking for reservoir quality sands beneath the top Latrobe unconformity. And everywhere in our study area, we're going to have deep water lake entrance shales sitting on top of the Latrobe, and that will form our seal. So if I think about seismic responses for the lake entrance and the Latrobe, the lake entrance is primarily deep water, low energy, distal shales, and pelagic snow. So there's not going to be much variation laterally or vertically in velocities and densities. And so there are not big reflection coefficients. And so my seismic reflectors within the lake entrance formation should be very low amplitude. If they have enough amplitude that I can correlate individual peaks and troughs on the seismic, they should be fairly continuous because we're in a deep water setting. On the other hand, the Latrobe, we would expect to see interfingering of sands and silts and shales as we're in a transitional zone between the continental deposits and the marine deposits. We would expect more significant vertical variations in velocity and density. Therefore, we should have higher reflection coefficients, and so we should have much higher amplitude on our seismic reflections within the upper Latrobe. So here's a piece of one of the regional seismic lines in our study area. The Pliocene is up here. The Miocene is this kind of chaotic infill. The area of the Oligocene is down in here. And hopefully, whether you look left or right, you can see that there's a different character between this area, about 1,000 milliseconds or 1 second two-way travel time, and down at about 1 1/4 seconds or 1250 milliseconds. We have fairly low amplitude. They're grays and light yellows, a little bit of black and a little bit of red, fairly continuous. And so I would suggest to you, this is the type of signature I might expect for deep water shales where I don't have much change in lithology laterally or vertically. But down here, slightly deeper, we have really black blacks and really red reds. We're getting much higher seismic amplitude, and I would suggest that that might be related to the interfingering of these transitional sands and silts and shales as we have different periods of minor transgressions and regressions. And if I look really closely, and I have 40 years of doing this, I can see evidence that some of these stronger reflectors have been clipped off or truncated, and that could be associated with erosion at the TOL, top of Latrobe unconformity. So I might suggest, just based on my regional expectations, that that top Latrobe unconformity is this light green line separating the lower amplitude packages above from the higher amplitude packages or lower amplitude formations from the higher amplitude formations. And then I have some faults that I can interpret and some more faults over here. And I think this is that unconformity. It steps up here, it steps up here, it drops down here. So even without any local well data, I can use the outcrop and the onshore well information, put together somewhat of a regional geological story. Then I can look at my seismic and put on my geophysics hat and say, what sort of response should I see for certain types of formations that I've been able to study onshore. And I might be able to begin to map out some of the key formations within this area. So as I mentioned, this green horizon top Latrobe unconformity is very critical in this basin because our potential reservoir rocks are beneath it, our potential sealing rocks are above it. And so when I have a local high, as on this structural high, I have a trapping geometry, I have potential reservoir, I have potential seal. The only thing I have to worry about now is, do I have a source rock that's mature and has hydrocarbon migrated from the mature source areas up into these anticlines. So that's kind of the regional story for the Gippsland Basin. Let me pause 2 or 3 minutes here and see if Max has a couple of questions for me.
Yeah, we can get started with Alonzo's questions. He's got a couple. He's asking, how much time do you spend looking at the seismic imagery relative to, say, other things you might look at?
Good question. That depends somewhat on how big of a company that you work for. When I worked at Exxon and ExxonMobil, I was a seismic interpreter. So I spent 40 plus hours a week looking at seismic wiggles. If you're at a smaller company, you may have to be able to look at the seismic, you may have to interpret the wells, you may have to do some of the regional geology. So the smaller the company, the more Jack or Jill of all trades you have to be. The larger the company, the more specialized you can be. And so a company as big as ExxonMobil or Shell or BP or ELF, you may be very specialized. We have people that work only seismic acquisition. We have other people that only work processing. We have other people that only do seismic. We have other people that do time to depth conversion. We have other people that do seismic attributes. So it somewhat depends on what your particular assignment is and how many people form the integrated team that's going to look at a place like the Gippsland Basin.
Mm-hmm. Hopefully that answers your question, Alonzo. Go ahead and ask another question if not. Yi-Ann would like some clarification. With respect to the amplitudes, what does a strong amplitude versus a weak amplitude mean?
Good question. The seismic waves that we send down into the earth respond to two main physical properties of the rocks, the velocity of the rocks and the density of the rocks. And so if I have a fairly homogeneous shale, I don't see changes in velocities and densities. And so I don't reflect back up to the surface very much of the energy that reaches that depth. But if I hit another area where I have embedded sands and silts and shales, the velocities and densities of sands are different from silts, and from silts they're different from shales. And so I would expect to have moderate to strong seismic amplitudes. And if you need more detail, I would refer to the first course that I mentioned that has the 34 lessons. And there's a couple of lessons. I don't have the lesson numbers in front of me, but probably around 9, 10 that talks about the seismic method and the basics of seismic interpretation.
Okay. Thank you, Fred. Those are all the questions I have at this point.
Okay. Let me go on and talk about the Barracouta field. If you do exercise one, maybe some of you have done it already, maybe some of you I can tweak your interest. There are 15 blocks in the offshore Gippsland area that you as a team would bid on. And if I was doing this in person, as I've done on a number of occasions, I might split the classroom into 5 or 6 teams and give you a certain amount of time to turn in bids. And then we see who the highest bidder is on the different blocks. The area that we're going to focus in on after the lease sale is where the Barracouta field exists. So if you're going back in time, as I'm trying to early exploration, you don't know that a field is out there. You don't know that there's hydrocarbons, but you're hoping and wishing that there are. So I'm going to kind of reveal some of the final answer, but remember, this is information the explorationist wouldn't have. So here again is the index map. The red oblong oval here is the Barracouta field. And in my training and upbringing and work experience, red means gas, and green, like over here, means oil. So Barracouta turns out to be a very significant gas field. Historically, it is the first discovery offshore of Australia. So before it was drilled in, I think it was 1965, there was no offshore wells. There was no knowledge that there'd be any hydrocarbons there at all. So let me go through the plate tectonic setting for you. Here's East Antarctica, here's Australia, the island of Tasmania. What will become New Zealand is over here. This is early Cretaceous. Let me go to the next slide. The same image that's blown up. So we have an extensional zone that's going to turn into a mid-ocean ridge over here. We have a transform boundary, and we have another rift that is starting to form over here. So here is that triple junction. This arm and this arm stay active. This arm is going to die in the mid-Oligocene, and so this is an Oligocene. So in the early Cretaceous, we had deposited the Strzelecki group. You don't have to worry about all these terms or how to say them or how to spell them. These are the earliest part of the Sin Rift deposits, largely clastic sediments with some volcanoclastics mixed in with that. It marks the initiation or the start of rifting. If we go to the late Cretaceous, we get the Golden Beach deposit. That's the middle part of the Sin Rift. And we get some coals that are deposited within the Golden Beach. And that's going to be our primary source interval. Then late Cretaceous to early Oligocene, we get the Latrobe group. That's the late phase of rifting, mostly clastic sediments. Again, we can get some coals, but not quite as significant. We are creating space faster than the sediments coming off the continent can infill it, and so we have an overall transgression or backstepping of the different depositional environments. The rifting ceased about 30 million years ago, and so we have this major transgression going on. And then in late Oligocene, we get the lake's entrance formation. This is the deep water marine shale that I mentioned. It's going to be a world-class sealing lithology. After the Oligocene into the Miocene Pliopleistocene, we continue to get deposition. There is some readjustment of the microplates because of some far field stresses, and we do get some of the extensional faults have reverse motion on them, and so some normal faults become reverse faults in the Pliocene Pleistocene. I can talk a little bit about basin evolution. In the Jurassic, before rifting started, we would have had normal thickness continental crust sitting on top of the mantle, about 35 kilometers thick. In the early Cretaceous, early Cretaceous, we start to get extension. Maybe the mantle's starting to upwell. We get rotational fault blocks, and we infill that primarily with non-marine sediments. You can think about the East African Rift system as an example. As we get into the later Cretaceous, more extension, the block faulting continues. We start to get marine sediments as well as lake and non-marine sediments. And then if it had gone far enough, we would have gotten a mid-ocean ridge, and so the Gippsland Basin would have been half of an extensional margin. but for the Gippsland itself, this extensional motion and spreading ceased before we had a mid-ocean ridge form within the middle of the Bass Straits. We can mention a little bit about the stratigraphy. Here's a stratigraphic chart. So we're looking at ages, 5 million, 50 million, 100 million, 150 million years ago, the eras, the periods, and the epochs, the onshore to the offshore stratigraphy over here. And there's a big break in the middle of the Oligocene, and this dashed pattern here is the lake's entrance formation. This pattern right here is the nearshore sands of the Latrobe group. This would be the fluvial to non-marine part of the Latrobe group. So we have the Strzelecki group, that's the earliest part of the rifting. The Latrobe group, which is middle to late. Then we have this major top Latrobe unconformity that's associated with the collapse, the cessation of rifting. And then we get the sea spray group on top. The bottom formation of that is the lake's entrance, which is our deep water shale that's going to be our sealing lithology. So if you do exercise number exercise number 2, that's the lease sale. And so we have blocks 11 through 15, 21 through 25, 31 through 35, and you'll have the lines that are labeled line 1 to line 9 going roughly north-south, and line A down to line E going roughly east-west. And you would have an opportunity to bid on the blocks and see which team ends up with which of the blocks. So our best leads will be places where this top Latrobe unconformity, the green marker, is structurally high. We have an anticline, and underneath green, we would hope to see higher amplitude reflectors, and on top of green, we would expect to see moderate to low reflection amplitude reflectors. And so this would be our potential hopeful reservoir, and this would be our potential hopefully exist regional seal. So I'll talk about the alpha lead. That's what we're going to be studying in the rest of the course. I've altered the block numbers and I've altered the line numbers so that if you're viewing the video and you haven't done the exercise yet, I don't tell you which of the 15 blocks we're actually looking at. So if you do the exercise, there are seismic lines and maps that you can print out. There's a Word document with instructions. And then after you've done that, and not before, there's a PowerPoint that shows the solution. So we can summarize the hydrocarbon systems. The source rocks are coals and coastal plain deposits in that Golden Beach subgroup. It's dominantly terrestrial plant origin, but it has high total organic carbon. And in the southern hemisphere, these coals generate more oil than coals tend to generate in the northern hemisphere. The reservoir we're hoping is in the Latrobe group, where we expect fluvial to near shore sands, and that's our primary reservoir. Our trap is extensional fault blocks that's associated with late Cretaceous to early Cenozoic rifting. And then we have the unconformity, and we can have some erosion that will modify some of those traps. Our seal is the lake entrance deep water shales, and that will be a very effective seal based on what we know about it from the onshore wells and outcrops. And our geochemist has done some modeling of hydrocarbon generation and expulsion, and the peak generation should occur for oil about 4 to 5 kilometers in burial depth, and for gas a little deeper, 5 to 6 kilometers burial depth. And for our portion of the Gippsland Basin, that should have occurred starting in the Miocene going up to the recent. There's another way that people often use to display what was on the preceding word diagram. I call it an exploration summary chart. Here's our stratigraphic chart, up dip to down dip. Here is our main formations. The upper Latrobe and the lake's entrance are the ones that we're most interested in. Here's the geological time scale. And then I have several columns, source rock column, reservoir column, seal, overburden, traps, and hydrocarbon generation and migration. So I'm displaying that oh, I got this backwards. The primary source should be the late Cretaceous. The secondary source should be uppermost Cretaceous to Paleocene. The primary reservoir is the early Oligocene and into the Eocene. We do have some potential within the Latrobe and older formations for some deeper reservoirs, but those are not our primary focus. Our best seal is the lake entrance, which would be up here. And then we have in brown rocks that have been deposited to push our source and reservoir down to the present day. We had some traps that formed in the late Cretaceous to Paleocene, and then the main traps formed in the Oligocene, mostly around the middle Oligocene. And the hydrocarbon generation for the deeper source would have occurred in the Paleocene, Eocene, and then for the shallower source, it would have occurred in the Oligocene, Pliocene, Pleistocene. So that's the presentation for today, lecture 2 and lecture 3, and a little bit on the regional geology. Gives us 15 minutes roughly for questions and answers. You can ask me questions on what I presented today or what I presented last week, or if you did some of the exercises, if you have questions related to that, I'll try to answer that as well. So I'll turn the microphone back over to Max.
Yeah, no questions so far, but we can give people a minute.
And the next webinar will be on Tuesday, the 30th, and we'll talk about lecture number 4, source rocks, and I'll probably give a little introduction to what the exercise would be like if you were to do that. So it looks like there's no questions. If you do have one, you can save it for next week, and I'll be happy to field questions about today's material next week or in one of the future webinars. I do appreciate everyone tuning in, so to speak, and Max, I appreciate your help in organizing it and acting as our host.
All right.